In this video, we'll look at the third long question from section 2 of the 2017 exam.
So here we have an elastic cord of natural length 0.5 meters, which is extended, and here in this plot we see the force needed to achieve a certain extension. There are two special points on this plot, point P and Q, where the cord fails by fracture. And our task is to describe the behavior of this elastic cord, or choose the right description. First of all, the relevant law is Hooke's law, which says that for a well-behaved cord, the force needed to stretch it to a certain extension is proportional to that extension with a positive constant of proportionality. So it's a linear dependence. And the linear function in the graph we see only until point P. So Hooke's law applies until P. And now comes the fracture at Q. In the possible answers, this is given in terms of the strain of that cord at the point of at the time of when the fracture occurs. So just a reminder of what the strain is. The strain is the extension divided by the natural length, and in our case, when the fracture occurs at Q, the extension is 0.05 meters, while the natural length is 0.5 meters, and that gives us a strain of 0.1. And that is a dimensionless quantity. So the right description of the behavior of the cord was under letter D, Hooke's law until P, and then a fracture at Q, which corresponds to a strain of 0.1.
In part B, we are supposed to calculate work done by stretching the cord by 0.05 meters. That means all the way to the fracture point. So can you think of a way work can be read off a force against extension graph? There is a very nice way of doing that, and that's when we realize that work is force times distance. Then the area under this fx curve must be the work done. It's the integral.
And we'll do this integral literally by parts. So first, this green part, the green triangle, it's 1/2, one side, height 0.15. Then this red rectangle, that gives us 0.2. And finally, the blue, which I approximated as a triangle. So we'll have an overestimate, slight overestimate, 1/2 base times the height, 30, and that gives us 0.3. And when we add these three contributions, we get 0.65 joules. As I said, that's an overestimate, but it's closest to one of the options given, 0.6 joules, which was option C, and our final answer to 3B.
In the next section, we use that elastic cord to make a catapult. To propel a mass m, by stretching the string, only half the string of the original string, that's important to note, we stretch it to maximum, and we want to know what the maximum speed at which this mass m can be propelled, what that speed is, in terms of the potential energy U, which we calculated in part B. So now we can gain potential energy half U by stretching this string to the maximum, because we only have half the string. And all this will get turned into kinetic energy during catapultation. So by conservation of energy, half U now is half mv max squared, the maximum kinetic energy possible. And when we solve that for v max, we get root U over m, the maximum speed, and option B. In section D, we now decide to double the cord, or more precisely use two cords of length 0.25 meters. And our task is to find the new speed, v2, the new maximum speed, in terms of the old speed when we only had one cord, not two. And to do that, we'll again consider conservation of energy. So what is the maximum potential energy when the two strings are fully stretched just before we propel the mass? Well, it's U, and it has to equal half mv2 squared, the kinetic energy just when the mass leaves the new catapult. So rearranging for v2, and then using the fact that Vmax from the previous section was root U over m, and we see root U over m here too, we can substitute Vmax, and we see that v2, the new maximum speed, is root 2 times the old maximum speed. And that is the final answer to section D, and in the exam, it was option D.